Thank you, Brian, and welcome everyone. Thank you for attending today's webinar. What I am going to talk about today is a little bit of an introduction about our project in general. What we will be talking about today is part of a large research project funded by the Department of Agriculture. When we talk about things that we have done, I want to make it clear that by we mean a large group of people, including 5 different universities, 2 companies. It is more than just the 3 of us. But this is funded by a grant out of the Specialty Crop Research Initiative. And what our project is focused on, let's see if I can navigate through. There we go. The project is focused on managing irrigation and nutrition in greenhouses and nurseries. And specifically, what we want to do is provide real-time information to growers about microclimate inside of the greenhouse or nursery, about how much water the different crops that people grow need, to help you schedule irrigation applications based on the requirements of different crops. And so what I want to emphasize is that we are focused on providing information to growers to allow you to make decisions. We are not interested in telling you how to irrigate. We are trying to get you the information that you need to help make decisions. So as part of this project, we decided to focus on the greenhouse and nursery industry, because within the whole arena of horticulture, we felt that the challenge was biggest within the greenhouse and nursery industry. The challenge is big because we have really intensive production systems where we have a lot of fertilizer use, high water use, frequent irrigations, largely because most of the plants we grow are grown in containers where you have a fairly small rooting volume, and that does mean that you need to be irrigating and fertilizing very carefully and on a regular basis. What typically happens as a result of that irrigation and fertilization is that you get leaching and runoff of water and nutrients, and as most of you probably know, there are stricter and stricter regulations around the country to reduce the amount of runoff from agriculture in general, including the greenhouse industry. So we feel that improving irrigation management in the greenhouse industry can have a really large impact. So what we are trying to do as part of this project is the first objective that we had is to develop wireless sensor networks, and I will explain in a minute exactly what that means, what that is. But what we want to be able to do is monitoring environmental conditions as well as crop water needs throughout a greenhouse or nursery, but also to be able to control irrigation as needed. So the wireless sensor networks are the hardware component of what we're doing. Having fancy hardware in place, though, is not very useful if you don't have a graphic user interface or software that helps you see the information that you are collecting and that summarizes all that information in a way that makes it easy for the users to make decisions about how to manage their irrigation. What Matthew is going to talk about in the second part of today's webinar is some of the work that we have done to develop guidelines that will help you make decisions about how to manage irrigation. And what Paul Thomas, in the third component of today's webinar, will be talking about is some of the economic impacts and management impacts that you get from having better control over your irrigation. So what I would like to do next is give you an introduction into wireless sensor networks. So this diagram that you see here represents a greenhouse that is divided up into 5 different irrigation zones, and within each zone we have what we call a node. So that is the little white box with the black antenna on top of it. That node can be used to connect sensors as well as irrigation valves too. So each node can have up to 5 sensors, and it can have 1 or 2 valves connected to it. Now these nodes are radio enabled, and that allows these nodes to send all of the information that is being collected through radio to a computer that you have nearby in an office. So this computer would then run the software that enables you to interact with the system. And that software includes irrigation scheduling software. It can include crop growth models, a database of crop production, and you can interact by entering information directly into this computer. But what this computer also does is that it generates a website. And that means that you can actually access your sensor network online through a computer anywhere, or using, for example, a cell phone. Any way that you can get online enables you to monitor and control what is happening inside of your operation. So I'll talk a little bit about the kinds of sensors that we're using. And that includes, well, the hardware includes both sensors, the nodes themselves, as well as irrigation valves. And after I talk about that, I'll give you an introduction into the software that we are using and that our growers that we collaborate with are using to actually use the system. So when we think about the sensors that we can connect to one of these nodes, part of that is just monitoring environmental conditions inside of a greenhouse or a nursery. So that includes light, temperature, humidity, rain, and wind. And if you want to, you can monitor leaf wetness. That can be a valuable tool in management of foliar pathogens. If you're inside of a greenhouse, the rain and wind may not be very relevant, but you can still monitor light, temperature, and humidity. And then more directly related to managing irrigation, you can connect soil moisture sensors, flow meters, as well as sensors that measure electrical conductivity, which can help with fertilization, fertilizer management. So this picture right here simply shows a setup of what a weather station would look like. So all of the different sensors are connected to this pole that you have in the middle of the picture, and in front of that pole we have a node mounted that is taking readings from all of these sensors and sends that information to your computer. What the three of us also think is a really important type of sensor to incorporate into irrigation systems is a flow meter that allows you to keep track of how much water you are using. That is not only valuable in my mind for your internal use, but it can also help you, I think, when you start interacting with policymakers. You can show them that you are keeping track of how much water you use, and you can show when you change irrigation practices what the impact is of that change in practices, and you can show that you are doing things to try to minimize water use. When you start installing flow meters that you want to include in a wireless sensor network, you just need to make sure that you have a flow meter that has what is called a pulse output that allows that flow meter to be connected to a node. Not all flow meters can do that. What I would consider to be the most important sensors that we use in our networks are the soil moisture sensors that you see here. So there are 4 different kinds that are typically used for greenhouses or nurseries. The 2 sensors on the left side of the screen, the 10HS sensor and the EC5 sensor, only measure soil moisture, so they tell you how wet or how dry your substrate is. The GS3 sensor on the top right measures water content of your substrate, but can also do temperature as well as electrical conductivity, while the sensor on the bottom right can do water content of a substrate and temperature measurements if you are interested in monitoring temperatures. So I just want to explain very briefly the operating principle behind these sensors. Basically, what you measure with these sensors is how the substrate and the water in that substrate interacts with an electromagnetic field. And the principle is actually identical to how a magnet interacts with iron filing. So as you can see in the picture, if you have a magnet and you put iron filings around it, the iron is going to orient itself along the magnetic field, while water molecules align themselves in a very similar way along an electromagnetic field. And when water molecules do that, that essentially causes a certain amount of charge to be stored inside of the substrate. And the technical term for that is the capacitance, very similar to capacitors that are used in many electronics. How much charge is going to be stored depends on the dielectric properties. And I don't want to get too technical here, but I just want to show you here how different materials interact with an electromagnetic field and how much electrical charge different materials can store. So the air that you have inside of a substrate can store very little charge. Likewise, the organic matter, so peat or a bark product, can store very little charge, while water, on the other hand, can store lots and lots of charge. So the more water you have inside of your substrate, the bigger the charge, the bigger the capacitance of your substrate. So typically, inside of a substrate, the charge that gets stored inside of that substrate depends on the amount of water that you have present. And that allows these sensors to measure the amount of water that is present. If people have questions about that, I can refer you to more technical publications about this. And so once you have these sensors, you need to connect them to a node. And sometimes when we talk to growers, one comment that we get as well, we really like the principle, but it is too complicated to put it all together. So let me show you how easy it is to actually do this. So the sensors need to be connected to a node. Well, this is a picture of the node that was developed specifically for this project. If you open up this node, what you see is, first of all, that the node has 5 ports at the bottom inside of the red circle. Sensors simply plug in to those 5 ports, so there's actually no wiring that is required. And then on the right side of that node, there is a relay with 2 terminals where you can connect a solenoid valve. So this particular node is designed for 24-volt AC solenoids, which is a typical solenoid that we use in greenhouses. And note that this whole node runs on 5 AA batteries, which typically last for about 9 months to a year, so it's very low power consumption. The batteries don't need to replace very often. In addition to this node, we have also developed a node that is specifically used for latching valves, which run on 9 volts DC. These nodes are more typically used in nurseries, more so than in greenhouses. The only difference between the node that controls DC latching valves and 24-volt AC valves is the area inside of the red circle, where there is, once again, 2 terminals right here. They are labeled black and red, and what you simply do is you connect the black wire and the red wire from the solenoid valve to the terminals labeled black and red inside of the node. So wiring all of this is actually very, very simple. So this is a picture of a node that is installed at Evergreen Nursery just outside of Athens, Georgia. You can see the node in a little bit more detail right here. So we have 5 sensors plugged in. Those are the 5 wires coming down from the node, and the sensors go into the e-GRO plants nearby. There is also a wire that goes from this node to 2 irrigation valves, allowing this node to turn irrigation in this particular zone on and off. We installed this node actually using a pot filled with concrete which makes it easy for us to move this node to different parts of this particular irrigation zone as needed. So we're not limited to one particular location within that irrigation zone. You can put it wherever you want to. So this node is collecting sensor readings from 5 soil moisture sensors that are connected to this particular node, and it sends that information every 20 minutes to a base station in an office nearby, and that base station, it plugs in using a USB cable to a computer, and this computer creates the website that the grower can then use to actually set up irrigation parameters based on his particular preferences. So a little bit about the software. This was developed by Carnegie Mellon University. They have done a great job in my mind. So the website is password protected so that only you have access to your irrigation system. And you can give different people different levels of access. There is an administrative level that allows you to do everything on the website. You can give people access as an irrigation manager, so people can set irrigation parameters, while you can also give people the access to just look at everything that is happening but not able to make any changes. But so through this website, the users can see all of the information that is being collected. It allows users to configure the nodes. I'll show that in just a minute. And you can determine or set up the irrigation protocols that you prefer yourself. And I want to again emphasize that you have full access to this website over the internet. So as long as you have internet access, you can make changes. So this is the login page, and I am going to ask Brian now to switch over to the browser that is running on his computer. Okay, so now we are actually so I think Brian is still trying to switch over to the browser. So Brian, this is still the.
I'm working on it. Just a second.
The PowerPoint. Yeah. Okay. So what I want you to do is actually go to the website so I can show you live what is happening or how you use the software.
Mark, can you hit the escape key to get us out of PowerPoint?
I will give that a try. So we can end the show.
Here we go.
Okay, so now what you see here on the screen is the browser. We are now logged in to the sensor web at Evergreen Nursery, and what you see here is the home page of that nursery, and I can move my mouse around, and if I place my mouse over one of these colored boxes that you see on the screen, each colored box is actually one of the nodes in the nursery, and you can get a quick overview of the current readings that are being collected by a particular node. The different colors actually indicate the different water content in the different irrigation zones. So green nodes, as you can see on the left side, indicate a wet substrate. Yellow, things are getting to be a little bit dry. Orange indicates that things need to get irrigated pretty soon, while red actually suggests that things are pretty dry. So we have a red node, 2 red nodes right now. It looks like part of the reason is that there is one sensor that isn't working correctly. But so this gives you a quick overview, and you can put a map of your own particular operation into the software very easily. That becomes the background for this. Then when you go to data view on the left side, that actually gives you more detailed readings from all of the nodes that you have. So if I click on show all locations right here, what is going to happen is that now it shows the readings from all of the different sensors that are part of the sensor web at Evergreen. So this is also the screen that you can use to get to the configuration of the nodes. So the nodes are simply named here after the different zones in Evergreen. They decide on the names. But if I go to zone G6 and click on G6 right here, that will take me to the configuration page of that particular node. So what you can do on this particular page basically is you specify which sensors you have connected to the node. So you do that from a drop-down menu. So you simply select from this menu which node or which sensors you have connected to the 5 ports on the node. So there is no programming that is required. And then you also indicate in this box right here the measurement interval, how often you actually want to collect data. So configuration of the nodes is really easy, and then one thing that is definitely a critical component of the setup as well is the irrigation configuration. So in this menu on the left side, if I click on irrigation, that is going to allow me to configure irrigation of the different irrigation zones in this nursery. So once again, there is a drop-down menu here where I can select the particular node that I want to configure. So we were looking at node G6 a minute ago, so I will go there again. So if I click on this node, it allows me to select which sensors connected to which ports should be used to make irrigation decisions. So right now we have clicked on port 1 through port 5, so all 5 sensors are going to be averaged, and based on that average, irrigation decisions will be made. And Will Ross, the grower at Evergreen, entered a set point of 22.5% water content. So what that means is that if the average substrate moisture content in this particular zone drops below 22.5, then that particular irrigation zone can get irrigated. But one concern that growers expressed from very early on in the project is all of the growers that we work with have a limited pumping capacity. So we have to make sure that we never open too many valves at the same time. So you can actually schedule when this particular node is allowed to irrigate using this bottom part here. So if I, for example, wanted this node to irrigate if the substrate is dry between 3 a.m. and 3:30 a.m., I can highlight that particular time period on the screen here, and that allows the node to irrigate at that time if the substrate is too dry. So I'm going to undo that again because I don't want to change the irrigation settings that the grower has entered here. But so this allows you to make sure that particular zones get only irrigated at particular times, and then you can see how many different irrigation zones could potentially be irrigating at the same time using this schedule viewer. So the blue areas that you see on the screen right here indicate when the different nodes may potentially be irrigating throughout the day. And at the bottom of this page, let me see if I can get to that. So this diagram at the bottom actually shows how many nodes might be working at the same time. So we have around 3 o'clock actually up to 5 different valves could be opening simultaneously, but never more than 5. So there is a lot of flexibility in how you manage your irrigation, and this kind of thing we always leave up to the grower. We may give advice, but we never tell a grower what to do. That never goes over very well. Besides, the grower is the one who has to make a living. I'm trying to now navigate up on this web page. Let's see if I can just go back to the previous page. And then if you really want to see how well the irrigation is controlled, there are graphs that plot the data from the different nodes. So we have been looking at node G6, which has a e-GRO crop in it. So we can actually click on this, and that is going to bring up a graph that shows the data from this particular irrigation zone, in this case from the last week. So you can see that actually the last time that this particular crop got irrigated was on October 18. So that is 5 days ago. And the different lines that you see in this graph right here, those indicate the substrate water content, which, as you can see, has been slowly decreasing over time. And the red dashed line actually indicates the set point that the grower has entered for this particular irrigation zone. So this gives the grower the opportunity to monitor whether or not the irrigation is working fine. So this vertical bar that you see right here, that actually indicates an irrigation event which lasted for 15 minutes, as you can see on the y-axis on the right side here. So this provides a lot of detailed information, and there are charts like this for each of the individual nodes that are present at Evergreen. So I am going to stop right here and see if there are any questions at this point. And after that, Matthew Chappell is going to talk about some of the work that we have done developing production guidelines and the impact of different irrigation practices on crop production and quality. So if we have any questions at this point, I would be glad to try to answer them.
All right, Mark, we have one question so far, and that is, how do we know what percentage of volume percent VWC to choose?
To me, that is something that we typically do that based on the experience of the grower. So typically, when we start working with a new grower, we initially simply install the sensors and we monitor substrate water content over time without actually controlling the irrigation. But what that allows us to see is we can figure out at which water content the growers typically start irrigating. And what a grower can do is, as we are monitoring the water content, the grower goes out to the crop and can say, well, I never want this crop to get drier than it is right now. At that point, you go take a look at the sensor readings, and that becomes your set point for irrigation. So there is no complicated science behind how we do this. We use the experience from the growers that we work with.
All right, doesn't look like we have any other questions, so we can continue on with Matt.
Give me 1 second to get situated. Okay, so what I'm going to talk about is a little bit more on the grower side of what we've been doing with this project, and mainly the impacts on crop production, crop quality, and also I'm going to talk or focus a little bit on the whole concepts of monitoring and then the transition from monitoring to control. So one thing that we all know is that greenhouses and nurseries pose a rather large challenge from an irrigation perspective. We do have very high fertilizer and water use, particularly in container situations, particularly in small containers that we find a lot of floriculture crops in, due to a limited container capacity for irrigation water to be held in. We have a highly diversified inventory. Many species and cultivars within species even have very different irrigation regimes. And then we have varied and overlapping crop production schedules. And all of this as a whole leads to some problems with irrigation management, and these are some challenges that we have with the system and that I will discuss throughout the presentation. And as Mark talked about, I won't hem and haw on this, but we all know that due to increasing government mandates and EPA regulations, we're going to have a larger and larger problem with leaching and runoff, particularly of nutrients. And then one thing that I will talk about, particularly in respect to McCorkle Nurseries, one of our grower partners, is how we've broken through some of the barriers with technology adoption. And a lot of that has to deal with just how people have thought about irrigation in the past. So one thing that we had to sit back and think about, and we talked to a lot of growers when we were trying to figure out this quandary or this problem, and that is what aspects of any new technology, and this doesn't matter if it's a potting machine or if it's a new irrigation technology, can help you increase your adoption rate. So first, it's got to have a quick payback period. This is something that Dr. Paul Thomas is going to talk about in the next presentation in about 25 minutes from now. The next is reliability of the technology and the system, and this is one of the things that I'll talk or touch on a little bit when I'm talking about some of these growers, particularly a little bit about Evergreen and McCorkles. And then the value of the information provided. Is that information valuable to the growers that we're working with? But all three of these things together lend themselves to ease of use. And with ease of use comes confidence in the system. I think Mark Van Ursel did a very good job of illustrating how easy the setup is and how easy the software is to use. But it really comes down not just to that, but return on investment, reliability, value of the information, all of that wrapped into one large package. So Mark talked about this. I put this in my presentation just as an intro for those who may have come in late. But what is a sensor network? Essentially what we're trying to do is to integrate a full range of soil moisture and environmental sensors. So it's not just soil moisture sensors. It can be anemometers, temperature, humidity sensors, all of which the goal is to provide real-time information. And for most of our growers, there's been a progression. Growers don't adopt this technology, plug it in, and suddenly they say, we want to control our irrigation. There's a certain level of trust that has to be garnished first by the system before people will allow it to control. And step one is irrigation monitoring. It's very simple. You as the grower monitor the soil using the sensor and this animation, which sends a signal through the node and then wirelessly to a computer. It will tell you, the grower, based on your past experiences, when that crop needs water, and then you will manually turn on the irrigation. And it's very interesting. In the case of Will Ross at Evergreen Nursery, this was about a 12 to 18 month period of monitoring before he started allowing control. In the case of McCorkle Nurseries, I do believe it was about 2 years, right, Mark?
We don't have the technology initially to control irrigation.
So it was about 2 years before McCorkle's really turned over the reins. A newer grower that we have in Georgia that I don't mention in this presentation specifically, Garden Design Nursery, went from monitoring to control in about 2 to 3 weeks. So as the system progresses and growers start talking to each other, it seems like it's being used for control much quicker. But step two is taking that step past just monitoring and now actually controlling it. So this is when the system is now connected to a solenoid valve, and the solenoid valve is then used to turn on and off the irrigation based upon that low threshold or volumetric water content that Mark mentioned in his presentation a few minutes ago. In this case, the system recognizes low VWC, it recognizes that water is needed, and it turns on and off the irrigation. Now, I'm going to jump right into the growers and actually go through some grower experiences. The first grower that I'm going to discuss is the one that Mark was just talking about in his presentation. Evergreen Nursery is a perennial grower for the most part. Most of their container sizes are small, anywhere between 2.5-inch cup all the way up to a two-gallon container is about as large as they go. Quick production cycles, so anywhere from a few weeks up to about 8 months is the max for anything they do. But they have a tremendous diversity of crops, particularly when you're mixing crops as well as container size differences within the crops. And in the case of Will Ross, he is an information addict. So the value of information was extremely important to Will. And in this case, it's one of the biggest things that he likes about the system. Like I said earlier, in the case of Evergreen, they went in 2010, the system was installed, but it was only monitoring substrate water content. It wasn't until 2012 that they started allowing the control of the irrigation events. And you'll see, Mark mentioned a lot of the specifics about Evergreen, so I won't get into it too much, but you can see here, this is their setup, and Mark had shown you a greenhouse. This is an outdoor cold frame, and you can see the two circles. The top circle is where the node is placed, and then the bottom circle is where a rain gauge is placed, as well as the sensors are in the pots. This is just another look at Evergreen Nursery. This is a heuchera crop. And on the left-hand side, and it might be a little hard to distinguish, but that is an EM50 node. EM50 nodes are used for monitoring only. They cannot control irrigation. And on the right-hand side, you can see a picture of an NR5 node, which is what Mark was alluding to in his presentation, that it has the capability to both monitor and control irrigation events. And one thing, and I'm just reiterating here, but in talking to Will Ross, one of the largest things that he likes about the system, in addition to just being able to see the data itself, is the irrigation scheduling capability. And a lot of growers, this tool was really driven for the most part by grower feedback. It's one nice thing about the system and its development is we've worked quite closely with growers to develop specific tools in the software package that they want. And in fact, we're continually revising those now as well. But one thing about Will's situation is that he was actually an excellent irrigator to begin with. So saving water actually what ended up not being as important to Will in the long term as the value of the information was. And this is one example of a benefit that Will was able to, and Evergreen Nursery was able to see. If you look at the left-hand side of this graph, you'll see what's circled there, which are individual irrigation events. And you see a quick uptick in the volumetric water content, but you also see a very rapid decline. And that rapid decline, Mark Van Ursel worked with Will very closely, and they determined that that was primarily due to a leaching event. So they were leaching a great deal of the irrigation water that they had put on that plant. On the other hand, on the right-hand side, you can see where they go to two separate irrigation events within one day. So essentially cyclic irrigation. And as a result of that, more of the water, particularly from the second irrigation event, you see the second peak isn't as high as the first. A lot of the second irrigation event's water was retained by the substrate, and leaching was much less. And what this has allowed is allowed them to, due to less leaching, be able to maximize their fertilizer longevity, as well as grow a generally more healthy crop with slightly less water. Okay, now I'm going to transition over to McCorkle's. McCorkle's is, I think, a nice all-around story. They were the first grower, one of the first growers that Dr. Van Ursel worked on this technology with. Even before I came on board at UGA 6 years ago, he was working with this technology. But McCorkle started off, we were using a system, and not quite what we have now with Decagon. It was a moisture click system. Just to back up a second, though, a little detail on McCorkle. They are a much larger grower than Evergreen. They have about 250 acres in production out of a 500-acre nursery. The 250 is actual production pad space. So an extremely large grower. And where we first initially started this is they gave us permission to use a 2-acre greenhouse. Initially, that greenhouse is about 300 meters from where the base station is. The node is able to send a signal to the base station. The developers, the hardware guys say that 1 to 2 miles, but I don't think we've ever tested it anywhere close to that far. We've never had a problem at 300 meters, that's for sure. But our first crop using the moisture click sensors before the Decagon sensors were developed was on hydrangea endless summer. This was just a preliminary study. It was side by side to compare water use between using soil moisture sensors to control the irrigation versus just using the standard grower practices. It's just a picture of the sensor that we were using back then, made by Dynamex in Houston, Texas. Moisture click sensor with a and what we found was pretty dramatic. Over not quite a whole growing season, but several months, they control plots on average were using about 13,350 gallons, and this is, I would say 400 to 600 square foot area. I don't have the exact number off the top of my head, but in the comparable areas we were using 2,300 gallons, so an 83% reduction in irrigation with no reduction in plant quality that was noticeable or measurable. The other thing that was very interesting at the end of this study, the control blocks that were irrigated more, obviously this was a controlled release fertilizer that was in the substrate these hydrangeas were grown in, and the EC was 0.94, so right at 1. Using the moisture click sensors, we reduced leaching due to less irrigation applied, so our final EC was higher. Generally with hydrangea, you're looking to keep an EC between 1 and 2, so this was right in the wheelhouse there. And then, like I said, plant growth and quality were both very good, very comparable. Now this isn't with this crop, but I just want to throw this out there. It is on hydrangea macrophylla, not on endless summer, but 2 other cultivars. And this just shows you, this is from a master's student research here at the University of Georgia, how much water in a 24-hour period do these plants actually use. So if you were to irrigate to field capacity, they're using only a fraction of the water in a 24-hour period that's present. And this explains to some extent the whole idea that we can reduce irrigation by 83% and grow a similar quality crop. So after the hydrangea, they were fairly excited, but still a little bit apprehensive, and they said, well, we need something other than just saving water, because the value of water to them is not that great. You West Coast growers that are online may be cringing at that thought, but on the East Coast, where most people pump out of the ground and their water cost is directly equated to the electrical cost or diesel cost to run that pump, it's a very small fraction. So what they wanted is for us to look at a problem crop, and particularly one that has disease issues. And they picked Gardenia jasminoides. In this case, back up real quick, this is August Beauty, grown in 2-gallon, trade 2-gallon size containers. And this, again, the first crop that we grew over about 1/4 of an acre, a little bit more than 1/4 of an acre size, so it's a fairly large crop, particularly for a production facility. And what we found was rather interesting. Our water savings were absolutely none between their irrigation control, or historic, and ours. That was completely due to the fact that I made a mistake and told the irrigation manager what we're doing. So he went and he looked at the flow meter readings from our soil moisture control irrigation plots and matched the flow meter ratings to what he was doing. And he did it very, very well. But one thing we noticed is this is a crop that, in this particular case, they were losing between 20 and 30% of that crop to disease. Our crop losses were virtually zero. I won't say they were absolutely zero, but surely 1% would be a gracious plenty that were lost in this study. So the crop health was absolutely excellent. The other thing that we found to be very interesting is that the finishing time was much, much faster. And this is one thing that Paul Thomas is going to discuss from an economic perspective. But I just want to give you the teaser of saying the finishing time was much quicker, spring instead of fall 2011. And that is what really got their attention. So it allowed them, in essence, to turn that crop quicker, come in with another crop, and utilize that square footage. And this is just a graphical representation. Like I say, Dr. Paul Thomas is going to talk about this more, but the yellow bars indicate their forecast sales based on when the crop would be ready. And this is based on historical trends from this nursery. And you can see the white bars are where actual sales took place. So all of this crop was sold by May of 2011, whereas they were actually expecting to have to hold that crop due to just typical crop production issues until as late as April of 2012. That's a tremendous increase in the growth rate and the health. So they weren't quite, show me once or fool me once, however the saying goes. They wanted to be fooled twice, and then they would actually start believing the second time we succeeded in doing this. So they came back in with the exact same crop. This time it was over about 1.5 acres of this production facility. So we almost tripled the size of the crop that was being grown. And this time we actually grew the crop even faster. So the crop start date, you can see down in the bottom left, was 6/18/2012. The ready date was supposed to be 5/1/2013. Plants, the picture you see here was taken on September 20th of 2012, and according to McCorkle's, the growers there, the plant was at a sellable state then. I also throw this picture in the top left in. One of the major issues with gardenia is the fact that they tend to get a pancake root system, so a lot of the roots grow toward the top of the container and the bottom of the container remains saturated. You don't get very good root exploration into the bottom of the container. But one thing you do if you use the soil moisture sensors is that your irrigation volumes are decreased, volumetric water content of that container is reduced, and as a result you tend to get much better root exploration. So at that point they were fairly well convinced and they were ready to go gung-ho and jump all over this, but they would essentially, the holdup was, and it still is to a certain extent, we're waiting for the commercial release of the system, and they're waiting for the commercial release of the system by Decagon. It's still in, even though late development, it's still in development. It should be released somewhere in very, very early 2014, but we were able to secure 2 more nodes, and they gave us a 4-acre greenhouse section that contained only hydrangea macrophylla. So what we've done with that crop, and you can see it here shortly after it was bumped up or potted up, is to, in this case it's still jammed, is they've grown Endless Summer and a few other varieties. I think there are probably a dozen or so varieties in here. They're both in 2-gallon size containers and 3-gallon size containers, and this entire 4-acre production facility is being irrigated using 2 nodes. Each node is attached to 1 solenoid valve, so 1 solenoid valve is controlling 2 acres of production space here. One thing that we have been concerned with in this greenhouse, if you look to the bottom left, they were using overhead impact sprinklers. and uniformity was a little bit of an issue, but we found that crop health has still been very good, and we haven't had any problems with this crop. Now, what I've been talking about up to this point is a little bit more along the lines of greenhouse / nursery fringe crops between the two. I did want to talk to you about some of the research that one of our graduate students is doing, Peter Allen. Very good work with a traditional greenhouse crop, which is poinsettia. And essentially what Allen is trying to do is work with a crop that has significant chemical input, in this case PGRs, to see if water deficit can be used as a substitute for plant growth regulators, which are a very expensive and laborious thing to apply to any crop. So like I say, essentially what he was trying to do is use controlled water deficit or volumetric water content of the soil to stress the plants and reduce growth, rather than using a chemical plant growth regulator to reduce growth. This is a system that he had set up. It is obviously a lot more complicated than the node we showed you, but this is a research-based system. This occurred on the campus of the University of Georgia, not at a grower facility. So he was using classic red rooted cuttings in 6-inch pots with a standard mix 80-20 peat perlite. In this experiment, he was using controlled release fertilizer. The plants were hand irrigated for 2 weeks after they were bumped up. That allowed them to start rooting out a bit, and then sensor controlled irrigation was used, set at 40% volumetric water content, which Allen had determined would result in minimal to no leaching. They were pinched at 33 days after transplanting at a height of 21.5 centimeters, had a target height at the end of production of 43.5 centimeters, which is a standard height, and growth tracking curves which are available for poinsettia. It's one of the big reasons why poinsettia was selected for this, is because we have growth tracking curves that were developed by the University of Florida for classic red, this particular cultivar. In order to get this software to work, you only need 2 variables. What was your pinching height and what is your target height? After that, it gives you a nice little curve like you see here. He had pinched at the 21, so that is your starting point. There are 2 lines. The bottom line is the lower threshold, and then the top line is the upper threshold. So if Allen had measured growth and growth was above the upper threshold, then a plant growth regulator and water deficit based on soil moisture sensing equipment would trigger some form of treatment. Either the PGR or drought stress would be induced. Here are all the different treatments. So the control is just standard practices, no PGRs and no water stress whatsoever. Water deficit, PGR as a spray, and that B9 and Cytocel were used for that based on label recommendations. The drench was bonsai, again based on label recommendations. And then the water deficit, what he would do is once they had reached that upper threshold in the growth curve, he would reduce volumetric water content from 40% to 20%. And there was no PGR applied to this. And that water stress was induced until plant growth had come back below that upper threshold and was within the optimal range. So you can see here, it seems like a very complicated and busy graph, but each one of these is an irrigation volume. The black dots are the control plants, and then the empty or white dots are the water deficit plants. You can see during this study, shortly after day 20, maybe day 22 to 25, there was a water deficit application, so the plants were allowed to dry down, or the soil was allowed to dry down. And then again, just prior to day 60, there was a drying event in order to reduce irrigation back down or reduce plant growth below that maximum growth line on the growth curve. So to track this graphically, what you can see here is the upper limit is the solid line. We're looking at that same growth curve I showed you earlier. And what I really wanted you to focus on is the yellow triangle. You can see that is a water deficit treatment. So it is above the threshold for the first 3 measurements, and then a decision was made to induce water stress. Thereafter, it dropped below or nearly at the line. The second water deficit treatment, or another water deficit treatment right around day 60, it drops below the maximum threshold line and stays there. So essentially, we've reached, or Alan was able to reach or maintain an optimal growth height without the use of PGRs, just using a water deficit or water stress. It's interesting to note as well that in the case of sprays, which is the upside down green triangle, our final growth, or Alan's final growth, was actually shorter or outside below the range of optimal growth. This is just a different way to look at it. This is plant height overall, and he's thrown in a picture so you can see size comparisons. But the control obviously was above that dashed line. The letters represent statistical grouping, so groups, treatments with the same letter were statistically similar. You can see that the control was taller than anything else and above the optimal line. The drench treatment was below the optimal line, as well as the spray treatment. Water deficit in this case was the only one that fell within the optimal growth curve. One thing that a lot of people had mentioned to Dr. Van Ursel and Alan during this experiment was, does this dretch stress actually reduce bract size? The only chemical application or dretch stress, only treatment in the study that reduced bract size was spraying, which, talking to growers, is one consequence of using spray-based PGRs. And then the other thing is, does it reduce canopy size? Another way of saying is growth index. The plant is measured in 2 perpendicular axes, and this is the basically square centimeters of that canopy size. Again, you can see that water deficit treatment did not negatively affect canopy size either. And then the final study I'll talk about is another one that Alan had done on poinsettias. In this case, PGRs weren't used. He wanted to look at, can various water deficit amounts or water stress levels lead to various growth rates. So again, classic red was used. This time, fertigation was used rather than controlled release fertilizers. Three target heights were actually looked at here. So 43.2 centimeters, 39.4, and 35.6. It was not expected that 35.6 would be achievable, but it's always nice to have something on the low range. Those were set at pinching. So from that point, this data was put into the growth curve program, and various growth curves for the 3 target heights were developed. The system worked just the same as before. Plants were maintained at 40% volumetric water content, and drought stress was at 20% volumetric water content. Measurements again were height. He also measured water use, shoot dry mass, bract size, and in this case internode length as well. And you can see this is a growth tracking for each one of the target heights. So you can see 35.6 centimeters in the top left was not attainable, although he was pretty close to reaching it. 39.4, which is the next highest treatment, he was able to actually have a final height of 39 within that range, just at 39 centimeters. 43.2 centimeters was easily attained using direct stress. And then the control treatment obviously was far outside of the range or optimal range for height parameters. When we're talking about final plant height, again, this is just a different way of looking at it using bars. You can see that the 35.6 and 39.4 were both statistically smaller than 43.2 centimeters or the control. One nice thing with this is that Alan has proven that you can not only reduce, but you can also control or keep that final height within a range, whether you're targeting 39 centimeters, 43 centimeters, or even slightly taller. And then this is just a photograph of the different sizes so you can see differences. There are striking differences, particularly on the 35.6 centimeter, but one thing he did notice is that bract size was affected on the low end. And I'll show a picture of that in just a second. One thing to keep in mind is Alan measured the number of nodes and the internode length. Internode length was affected by the direct stress that was imparted upon these plants, but the number of nodes that were produced was actually not affected. So what the direct stress does is it shortens internode length, which a lot of people already know that principle. This is the bract size, the final bract size for each measurement. This is just a representative individual. You can see 35.6 is considerably smaller, but the 39.4 centimeter and greater were all deemed to be saleable plants, even though the 39.4 is slightly smaller bract size. So essentially what Alan has developed here is a new method of controlling poinsettia height. It's still in the developmental stages, but he feels very confident that in the future it does have some applicability, and I do tend to agree with him. One thing to keep in mind, though, that severe water deficit or water stress can also decrease bract size. One thing to consider, though, is that spray treatments similar to severe drought stress also reduce the bract size. So it's not something that's just based on water deficit. PGRs can cause it as well. And then for more information, just wanted to let everyone know we do have a website, which is smartfarms.net, not .com, but .net. And coming soon, we're going to have lots of information on self-guided learning modules that you can walk yourself through, which will be in the Knowledge Center. And with that, take any questions you have real quick. Don't have a lot of time. Need to turn it over to Paul.
All right, this is Brian again, and there are a few questions that people would like to ask. Let's see, the first one, do you have any suggestions for greenhouse vegetables where irrigation may be required every 10 minutes in high light conditions and watering cycle times, maybe 1 to 2 minutes?
I am not a vegetable person. Mark, would you like to comment on that?
Well, we haven't done any work with greenhouse vegetables, but we have worked with a snapdragon grower in Maryland. He does cut snapdragons in perlite bags, and when our colleagues at the University of Maryland started working with this grower was convinced that he had to irrigate his crop 9 times a day. Once they actually started measuring how much water was present in his perlite bags, it turned out that he could reduce his irrigations to typically as little as 3 times a day, and he got much better quality as a result of that. He resolved botrytis problems in his crop. had better shelf life for his cut flowers. But so what our system can do is if you set it up for continuous monitoring and control, these nodes can irrigate up to 100 times a day if you want to. That is not a problem with this technology.
All right, so another question, is the solenoid valve controlled by time or by water content or water flow, I would assume?
The solenoid is controlled by the sensor readings or volumetric water content of the soil. That is the ultimate control. You can set it up as a time system. So if you would like to switch over to a timer base, that option is available. But in general, the goal is to turn it over to what we call local control, which means the soil moisture readings that are being collected by the node sent to the computer as well as the software, it averages that. If the average falls below the threshold, then an irrigation event is initiated. One thing that Mark in particular is working on for future applications, particularly ramping up the scope as far as size of the area that can be controlled, is using modeling. And if you want to touch on that real quick.
Well, I'd like to say a little bit more about how we typically control the irrigation. So ultimately, it is based on substrate water content, but you can program these nodes so that they only check during certain times of the day whether or not the substrate water content is below the threshold. And that is something that our growers absolutely insisted on, because the growers have to make sure that they don't open too many valves at once. So you can say, this particular node is allowed to irrigate between 7 a.m. and 8 a.m. and then the node during that period will check to see if the substrate is too dry, and if it is too dry, it will irrigate, but only during that specific time period. So, combination of timer and sensor-based control, but the decisions are ultimately made based on the sensor readings.
Okay. There's a question about sensor placement on the tips and types of media effects, like how much the media might affect the sensors.
Well, I can talk about sensor placement. Um, Done a lot of work, and John Leacox at Maryland has done a lot of work, particularly John, on large container sizes. But you essentially want to place the sensor into the root zone. Some people go at a 45-degree angle directly below the root ball, and that is through the top of the pot, through the soil, and into or below the root ball. You don't want to place the prongs flat. You want to make sure they're vertical in orientation. But above and beyond that, the second option that some growers use, particularly when you get into 2-gallon or 3-gallon size plant material, is they actually go through the side wall of the pot and they make a slit and insert it through the side wall of the pot, particularly on a smaller sensor or a larger container. It allows you to get the sensor lower into the root zone of that container.
All right. Another question is, can this system be used in young plant production, like in propagation?
We have not done that yet, and I'm not going to comment too much on that. But currently, no, we're not using it in young plant or liner propagation.
Okay, and the last question I can actually answer. The question was, will this webinar be recorded and posted for future viewing? And yes, it will be. It is being recorded, and it will be, posted on e-GRO.org for everybody to view. All right, our next speaker is Paul Thomas, but before we get Paul on here, I did promise everybody a couple-minute break, so if I think we might pause for 2 minutes and give people a chance to get up and stretch their legs if they need to.
I went 6 minutes too long. That's all right. I'll try to go 6 minutes fast. Let's see if my mouse works here. I'm not a pad. Take my computer with me.
By all means. There's your computer right there.
I would leave it. I would leave it in there. I'll put it back in my office. I've got an agent training. 47 minutes.
Thanks for participating.
How do I mute and unmute?
Because I would not touch anything on the control panel.
Okay.
Brian will take care of that.
All right.
Remember last time you touched the control panel? We ended up rebooting my laptop last time.
How do I make it go backwards?
Backwards.
In other words, I need to go back 3 slides. Down here?
I would just use the back. Yeah, you can down there.
Yeah, because I'm going to use the mouse. I'm a mouse guy. Very good. Okay. All right, we'll just go from there. All right. Battery. We'll be good.
49 people. I assume Brian can get that to us. It also will be nice, and we can post a link to the e-GRO on the.
Okay, my clock says that's been 2 minutes. So without any further ado, we'll continue on with Paul Thomas. Paul, it's all yours.
Okay, thank you, Brian. I'm just grateful to be invited here because I'm pretty excited about this project. In presentations that I've made around the country recently, those growers that have sat down and talked with us have caught on to the fact that this system gives you a lot more control and a lot more ability to make the kind of decisions you need to make with some accuracy. And that's really, really critical to this being worth the money that you're going to pay to implement it. So what do we do with this? Does this thing work? Does it provide itself enough benefits that it's cost effective? Is it worth your nursery or greenhouse around to implement this particular thing? Well, the only way you can measure that is to know where you are at the present time. And so Mark talked about flow meters, and I want to reinforce this because most growers I talk to do not have these. It's going to be very hard for you to look a legislator or even your accountant in the face and say, this system has paid for itself, look at all the water I saved, look at all the labor I saved, if you don't have your baseline measurements. So before you invest in the control part of this system, do that monitoring that we talked about with the preliminary part of the system, get an idea of what kind of water use you're doing, and start documenting how many labor hours are involved in watering, how many labor hours are involved in repair of irrigation systems or moving things around, and start documenting the costs of the raw materials that you're providing, so that when you finally get around to asking the question about is this cost effective to implement the new technology, you'll have your baseline material. I want to point out too, I just recently gave a talk in Indiana to a bunch of wonderful growers who paid really close attention. Indiana went through a pretty severe drought, and as Texas, Georgia, Indiana, and other places in the country have found out, once a community goes through a drought like that, legislators are put under pressure for water conservation, to be able to guarantee to citizens that there will be fresh potable water available to them. And so they turn around and start asking questions of nursery and greenhouse owners who are, because of what they see driving by, presumably heavy water users. and they asked the question, what are you guys doing to conserve water? Well, these flow meters are one of the best ways to document where you were and how these new systems are conserving water, so that when it comes time for the next drought to be around, you're not going to be one of the people scrutinized. You'll be able to show them hard facts and figures of what you're doing to conserve water. So there's a nice little legislative benefit to being able to say you're part of the solution rather than part of the problem. The nice thing about flow meters too is that the data is acceptable to legislators. We're not talking about acceptable to scientists. That's already taken care of. But even a legislator is going to believe a flow meter. So it's something that's fairly easy to use, and people will get it if you give them those figures. All right. Just a quick idea. Mark talked about the type of flow meters that you would connect to the sensors. This is an example of one of them. They're not that difficult to install. A plumber can put one of these in, if you don't do this yourself, in probably an hour and a half. All right, I'm going to move right on to the next talk. So my point today is to talk to you about the impact that this has had on the growers that have upgraded their technology. How did they feel about it? How did it go? Where did they take it? The first thing, I'm going to make a statement, and that is that wireless sensor-controlled irrigation systems will save you money, time, resources, water, and will provide you a high-quality crop. We've seen this over and over again in the demonstration activities that we've done. The question is, which of course is most important to you? Which of those aspects are important? Just a quick map here showing you where our test sites are. We have quite a few of them in Maryland, a couple in Georgia, one in Tennessee, and one up in the Ohio area. And these are all areas where our partners are. We're all doing research closely related. So it's not just being done in Georgia's backyard where we're just dealing with Georgia's environment. The types of results we're speaking about have been seen all over this portion of the country. I know that Decagon has a very extensive testing system for all of their test equipment and all of their sensors out on the West Coast, and they do a very good job of covering a lot of territory and making sure that the equipment works in a wide variety of soils and all that. So we're pretty confident ourselves about the quality of the system. So we had some demonstration sites, and some of these goals I want to go over again just to give you an idea that we weren't looking at this as a quick way to present some cool technology and get a paper. We were more concerned about, is this going to be a technology that just doesn't fit, is too hard to work with, and ridiculous for someone to truly try to install in a nursery, which has happened before? Or is it something that is basically grower usable and is going to provide immediate results? So our team, and this again is multi-university, worked out a lot of the basic implementation issues, such as where to put the sensor, how deep, what angle, how long does that sensor last, what are the things that can happen to a sensor that might make it not work, such as animals chewing on wires, things of that nature. The second thing we've been trying to work through over the last 2 years is scaling it up. It's one thing to set up 12 pots in a greenhouse and test a sensor on 2 lines or 3 lines and be able to say, oh, this works great. As you heard from Mark and Matt, we're now working on the 1 acre, 2 acre, 4 acre scale, and things are going very, very well. So we're very confident that scale up is possible, and that growers wishing to move from a trial system to maybe operating 30 or 40 acres of a nursery with the proper setup isn't going to have any problems with difficulties with extra system parts. Another aspect of this was, are these systems capable of having some mobility? Can you move them around? I don't know of a single nurseryman that grows the same crop in exactly the same place, and in greenhouses crops can turn over in as little as 4 weeks. So the idea that you permanently install something in a greenhouse or nursery would not make sense. It's got to have some mobility. It's got to have the ability to be picked up, moved around, applied to a different crop, and still have the functionality that you count on. Another thing that we've looked at over the last 3 to 4 years, and Mark has done a great deal of work on this, is sensor reliability. As with any startup, 6, 7 years ago, these sensors worked great, but maybe the coating wasn't the best, or the amount of flexibility in the sensor lent itself to being broken. These types of reliability issues were reported back to the company, and there's been a lot of changes, several generations, to make sure that that sensor is tough and nursery ready, ability to be handled by people and installed in a nursery setting where things aren't exactly calm and peaceful. And the reliability now on these sensors is very, very good. Data interpretation. It's sometimes very difficult to look at a graph and see a bunch of lines or a bunch of dots and really get an idea of what's going on with that system. And with our friends at Carnegie Mellon and University of Maryland, and with Dr. Van Urssel's assistance, there's been a great change in how we present the data interpretation and how the grower interface has been evolving. In fact, that evolution is occurring right now. One of the reasons we are not yet rolled out on the control aspect of the system is they are working on the final touches to the grower interface to make sure that it integrates all of the things they want it to do, but in such a way that the average person operating a nursery can easily access things, understand what's going on, and visually how things are changing in their nursery. Now, the part of the projects that Matt and I are more concerned with is not the technical side, but looking at how, if we install a system, that we involve management changes. How is a system, a nursery, for example, going to deal with this system? Are they going to fire people? Are they going to relocate people? Is it going to allow them to free up key personnel to do other things that are of more value than managing an irrigation system? So we've tried to track and monitor and observe what type of changes occur in the nurseries that have adopted this technology. The second aspect is looking at perceived value, asking the question, above and beyond just the technical data numbers that are provided, are there any other general values that are added to the nursery when this technology is adopted? And one of the values that you might look at might be more time for management, or it might be more peace of mind, less worries about, are my crops drying out while I'm out of town, that sort of thing. The last, of course, is the one that almost every grower approaches us within minutes of hearing this talk, and that is, what's the payback period? How much is this going to cost? What's the economic impact on my company? Is it going to save me money? Is it going to actually make me money? How much is this going to hurt me? So we've actually been able to work with a couple of growers who have shared with us their economic figures. Now, let me stress again that one of the things you have to have before you do that type of a study is those figures in the first place. All right, you have to be able to say, we know where we're at prior to doing this new technology setup. All right, I'm waiting for it to change over. So once we sat down with the growers, I'm going to give you some quick statements here. The potential benefits that we found were that people did see water, energy, and labor savings. Of course, we already talked about some increased yields, reduced losses. There was a reduction in management time that was dedicated toward irrigation issues. And of course, Matt talked about this accelerated production time. All of these things, the water, energy savings, increased yield, reduced losses, and all that, can be estimated on what we call an annual basis. Now, the minute you start talking about reduced time for a crop to be on a bench, those schedules are very, very difficult to do on an annual basis. And so we have to look at changes in production, in other words, dollars per square foot per week, and ask the question, can we change that or amortize that to an annual basis so that a CPA can actually say, by changing this irrigation system, we increased the dollars per square foot or the penny per week in this particular part of the facility. Those are the kind of things a CPA needs to know. And was that a good use of our money? Was the cost or return on investment worthwhile? We can also look at those system cost and payback numbers as a function of a yearly payment. In other words, how much on a per year basis, if a system is going to be alive and well for 15 years, if it has that type of lifespan, how much is it going to save me per year over that 15-year period? So these are the kind of things that an accountant would look at to be able to look you straight in the eye and say, economically, on a financial basis, this is a good decision or not. So we are going to, as time goes on in this grant, present to you some of these economic case studies that will give a very, very clear idea of what these savings are. I'm going to show you some data, first of all, that came from McCorkle's nursery. I just want to point out that McCorkle's has been highly successful, family-owned, second-generation management because they are very meticulous about the financial records they have, about the resources that they spend, about the square footage that they have crop on and how it's being managed. And when we talk to them about the specifics, and I'm going to try to go back here, I don't know why that advanced, we asked them what was important to them and tried to help measure that as we went through the experimental systems. Okay, all right. We talked a little bit about the Gardenia radicans crop. This has been an industry problem crop. It's not just a problem that McCorkle's had. The traditional way to grow gardenias was under a very high volume of water. Given the summer heat that we have in Georgia and given the bright sunshine, these crops are high water users and they have the potential to dry out very quickly. And so the growers compensate and irrigate these very heavily. Now, as a result of the high disease pressure that we have here in the South, there was always a fairly high amount of shrinkage. It might have varied between grower. Perhaps they used different soil products or irrigated a little bit differently. But there was always this issue of crop loss. Matt showed you this particular diagram that we sat down with Chris McCorkle and said, map out where this crop would be sold. He showed us the actual sales figures for previous years, and this is what, of course, it would look like for forecast sales. You would see a majority of product come to fruition as available in middle of March. It's ready for sale, and the actual sales would come in other words, the contracts would be signed between May and October. Then there would be a dearth of contractual agreements as the season chills down and landscapers are purchasing less, fewer projects are being established, fewer garden centers are buying things. And then it would pick up again in April, February through April with contractual agreements. So this is what they would normally expect to happen for one particular crop. Now, I want to point out that the numbers we're about to show you are the actual production cost data as per Chris McCorkle. He was very generous in sharing with us the actual numbers. All right? The distribution of sales was determined from actual experience before and after the use of the sensor system. So basically, we had a chance to look at the books before and after. Our experiments on his facility show that overall there was a 50% reduction in sale time, as Matt pointed out to you, and a very strong production loss reduction. Monthly expenditures, the sales themselves were discounted back to month 0, and the present value of expenditures and sales. What this means then is that we're looking on a per year average basis to make it make sense to an accountant who's trying to figure cash flow and all the other aspects that you would have to worry about when investing money in new technology. Our losses were assumed to be constant per month beginning month 6th after the sale process occurred, and this was just to avoid having artificially high numbers. We tried to have a very conservative, realistic aspect, even though as things are being sold out the door, we weren't tracking any inherent losses from a pot being broken, things of that nature. All right. Matt showed you this diagram, and I want you to think about this two different ways. You can see that the actual crop availability came in very early, and because of the higher quality crop, very, very nice and mature filled cans of material, they were able to sell that crop right to the end of May, a very, very fast return, because quality sells. Everyone knows that. If you've got a really good looking crop, people are willing to put money in it. And so all of the crop was sold. They didn't have a loss of 2,000 to 3,000 plants within that crop. They sold almost all 20,000 plants in a short period of time. Most growers would be very, very happy with that. And they made a little extra money on the crop based on their expectations. That turned into what we would call monthly or yearly profit, and everybody was happy. But that's not the real story. The real story is, what can you generate on a square foot basis per week in the land or growing production space that is no longer being tied up with that particular crop? Now, greenhouse people know that the name of the game is turnover. How many crops can I generate on a per square foot basis per year? In the south, we're likely to get 3 crops of bedding plants turned over in the spring, and if we're really, really lucky, 2 crops in the fall. Now, with a nurseryman, some of those crops, especially longer term, larger trees in larger containers, larger caliper sizes, they may be sitting in a nursery field for 3 to 5 years, or if it's in a container nursery, it might be 2.5, 3 years. But even so, if we can reduce the production time for either greenhouse or nursery crop by a week or by a month, it's going to free up that space that potentially can have a new crop in place, perhaps a different crop that can be sold on a relatively quick basis. That means more dollars of gross income per square foot. And when we look at the potential for gross income on this diagram, I think you can see we've almost increased the effectiveness of that nursery by 150%. We're able to, if we were to say have 2 other crops that could grow in a 4-month period, which certainly bedding plants would fit into that, or maybe some other fall crops, that McCorkle's now has the potential on that land to turn more crops over, whether they're short-term or long-term. This is what every grower wants to see. They want to have that ability to generate more product per square foot. It's the quickest way to make real profits. There's a lot of things you can do to save money and to cut costs, but generating more plants per acre over a set period of time is the #1 way to increase profits. And this was a wonderful example that that works. Now, let's take a look at some of the financial aspects of it. And again, these are real numbers that were provided with the knowledge of Chris McCorkle, and were worked on by Eric Lichtenstein, who is our ag economist at the University of Maryland. I want you to realize that the payback of this system, the payback of the actual cost of the nodes and the network wires and all the things that would be necessary to make this system work, was less than 1 month. I want that to sink in for a minute. What other investment can you put $5,000 down and get $5,000 back in savings in less than a month. Other than the drug trade, I don't think there is one. And so it's something to pay attention to. These are not expensive systems. These are wonderful investments for a nurseryman or a greenhouse person. So let's start at the top of the page under annualized revenue for the acreage that this crop was sitting on, for the square feet it was sitting on. For just the crop with no sensor system in place, traditionally they were able to generate about $66,000 of gross income for that location. With the sensor-based irrigation system, that exact square footage generated $145,505. Same space. We're not looking at production time here, just looking at a spatial how after we look at their overhead expenditures, which aren't listed here, all of their direct costs, the sensor system costs, the whole bit, the annualized profit for that square footage that this crop was in was about $35,000, maybe $36,000 without a set of sensors in place. When we had the set of sensors involved last year, they were able to generate a profit of $91,000 for that square footage. Remember, this is a fraction of their nursery, but they were able to basically triple their annualized profit from the combination of reduction of losses, improved quality, and the rapid return on those sales. Again, if we look at the shorter production time, that contributed to quite a bit of the sales production, and from the higher quality in the whole bit. And then if we work that back, it was $38,000, about a $3,000 increase just based on having the system sensor there. Now, annual square foot was $1.79 with no sensors. It was $4.59 per square foot with the system irrigation in place. And what that generates down to is 156% increase in profit per square foot. I want that number to sit in there. When we look at that money, that increase in sales, the fact that we don't have all the expenses of it sitting in the field, we don't have all the overhead, we don't have any of those expenses that tie into it, that's a huge, huge return on investment. If you ask the question, where again would you get that kind of return on investment? I don't know of any stock that you could count on seeing much more than an 11 or 18% return on a good year. The type of return that McCorkle's is showing here is pretty phenomenal. One of the things to consider is that this payback period of 1 month, it means that when you go to a bank and we present, let's say a year from now, these case studies, it should be fairly simple, even if you're investing $50,000 or $60,000 in a system that'll operate 50 to 100 acres. It should be a simple matter to be able to show the bank these types of savings and returns on investment from not just McCorkle's, but we'll be showing many different types of nurseries and greenhouse production systems. You should be able to very easily justify that bank to give you a loan for this type of technology. Something to consider then, once you pay for that system, even if it took a year, all the increased profits, all the advantages that you have on that system go forward for the next 14 or 15 years, whatever the life of that system is. Another thing to think about, and what isn't shown on this graph, because we didn't want to be accused of padding the system, if we go ahead and put a second crop on that square footage that was sold, in other words, the space is now open and we can generate a whole new crop. If we had planted that crop and put the profits from that crop into this projected profit margin, the profit increases could be as much as 10%. Now, McCorkle's did not do that. There's not enough time to quick throw a crop in, have a market, have it sell, and all that. But given a year, given some planning, given the comfort of knowing that, yes, we can do this, and we've done it 2 years in a row now, now we can say, what else can we reliably put in that space that we know is going to be made available because we've improved our production system? Once that occurs, we will be able to document the increased profit per square foot based on that extra crop that's now been put on that system, or however they want to use it efficiently. And I think you'll find the return on investment would be even greater and even shorter. So it's a pretty amazing thing. And when we see numbers like this, and we see the improved quality of, say, snapdragons at the Bowers up in Maryland, it's why we get so excited about this. Using less water in a controlled way, matching what the plant's needs are with this system, is the way to go for better profits. Okay? Now, one of the things as an extension always curious about is whether or not these nurseries are actually adapting to this, and how are they, in effect, adopting this into their management. Well, I want to encapsulate that McCorkle started out using 7 sensor control zones in a small 2-acre area, and have now moved up to a 4-acre area with only 2 sensor controlled irrigation zones. So what does that mean? It means that Chris McCorkle has become comfortable, can understand the system, and is confident with proper placement of the sensors in the pots in the right locations. He can now get a good grasp of irrigation control over a larger area with the same number of sensors. It means he has faith in the system, and he's applying it over a much wider area, which means less cost per square foot using fewer sensors. But that's because he's got this management comfort as to how far he can push it and how well the system reacts to managing large areas, how much variation is there. So it's a very, very interesting story that's being told there that we're changing. At Evergreen Nursery, again, this is a 30-year-old business. They have over 200 plant products, a lot of variation in the system, a lot of species. Evergreen Nursery has 150 irrigation zones, averaging across about 1/7 of an acre, because they have all kinds of small 4-inch ground covers and perennials that they produce. And so their prioritization was mobility. They had to be able to say, X crops, these 5 crops are the most water sensitive, or the ones that we're having the most problems with keeping at proper moisture levels. And those are the ones we have to use the system on this month or this 6 month. For them, mobility was very, very important. This is a picture of a field day that we had at Evergreen Nursery. Dr. Van Eersel put this together. We invited a bunch of growers from the state of Georgia and a couple of county agents and a couple of university people to come and see the systems and what they could do. As part of that interview, they talked to Bill and his son on what they thought of the system after they've used it for a while. And these are the things that they told us were much more important to them than just the money, just the cost savings alone. They said peace of mind was more important, because they could get on an iPhone or simply look at their computer screen in the office and know exactly where things were at in their nursery, not have to get up and drive around the facility or wait for some employee to call and say, we've got a bay of wilted plants. So it sets down that stress level, and allows them to feel like they have a sense of what's going on. That's very, very important to a manager. The second thing that they pointed out is it gives them increased crop security, the knowledge that the crop will actually grow to fruition. Because the system is automated, there's less chance of employee errors. There's less chance of someone forgetting to throw a switch or someone forgetting to apply the irrigation system to that last 20 acres down at the bottom of the field. And so there's this sense that at least they know things are going to be watered on time. All they have to do is monitor their screen. If there is a problem, it's going to show up right away. They don't have to worry about somebody not doing their job and things showing up a day later. The next question they said was system reliability, and they were very, very pleased with the reliability, about the consistency of the data, about the ability of the system to be moved around and still work and still be functional. And the combination of those three things gave Bill and his family more owner time to worry about sales, more time to worry about shipping, more time to worry about perhaps IPM programs or some other aspect of the business that wasn't getting their 100% attention because they were worried about plants drying out. So it was a godsend from his standpoint. It freed up manager time. And the question is, what's manager time worth to you? Okay. In terms of adoption, Evergreen recently changed a big area of their production site. They went ahead and leveled a 2-acre site and rebuilt these frame structures with the Saran to accommodate the new controlled NR5 sensor system. And they were able to reorganize some of the crops they use based on water use and use fewer sensors to control more square feet. Basically what they did is they redesigned their nursery in this area to match the capabilities of the technology, to maximize the benefits of that technology. It was a nice undertaking. They did a really, really nice job. You can see a picture of this. And it's going to transform their company from having small, disorganized hoop houses to having larger areas that are sensor controlled and are designed specifically for maximizing the efficiency of irrigation. Really interesting changes in design. The last one I want to talk about relates to smaller growers. I know there's a lot of small growers out there, 1 or 2 acres. They may have greenhouses, they may be specialty crop producers, and the question that smaller growers always have is this technology something that's going to have any meaning to my size of operation, or is it just something that the big growers can take advantage of? Well, Garden Designs Incorporated in Danielsville, Georgia, it's a fairly new operation. They've only been in place 7 years, but let me explain, they grow Japanese maples. So it's taken them 5 to 7 years to even start growing sufficient stock for them to go to market. They have about 5 acres of production. It is a husband and wife operation, but the husband and wife also have external employment. The way it's described is this was a hobby business for when they retire. Okay? So they came across information on our system, had a chance to talk to Dr. Van Ursel and some of the other team members, and asked to be part of this trial. They were given a NR5 node and had 4 10HS sensors that they installed in their container production area at their facility, which you can see here in the picture. The gentleman did most of the work himself. He was able to install all the equipment fairly easily. In love with it, basically realized that he could start controlling and visualizing what was happening in his nursery using an iPhone. And so he was able to literally travel around the United States as part of his job. It may surprise you, he's a Delta pilot, and he's able to land in LAX, go to the pilots club, whatever they call it at the airport, and call up his iPhone and see what the irrigation situation is at his nursery. And he's enjoyed this so much that he's turned around and decided that the information that he's getting from these sensors to pretty much control the majority now of his irrigation in those production areas. So a very, very fast turnaround from looking at the system, deciding he understands it, feels like he can work with it, move it around, make it happen, to loving it and spreading it out and making it work for his entire nursery. Okay? So in this particular case, he is now using the system to control his 2-acre and is basically telling us that this is making the management of his operation quicker, much easier, and it's freeing up his wife's time to manage more of the sales and promotion end of the business. It's providing more owner time. That's the take-home message for this. All right, we're about to finish up. All I want to do is say that from our current studies, we've seen that the system supports the hypothesis that we can get better water management, better crop quality, and reduce losses. Done deal. We have reduced production periods, which was a surprise, but we're doing this over and over again because we're finding that overwatering is a very common cause of crop delays. And the last thing to know is in our demonstration projects, growers are quickly adapting to it. They're grasping the meaning of the data. They're taking leadership themselves in expanding the control reach of the system. So it's being proved in grower sites that this system is changing not only their behavior, but how they do the management of their irrigation in the nursery or greenhouse. And we think that's pretty exciting data. Brian, with that, I will finish up.
All right, Paul, thank you. We do have one more question that came in. And it says, did you measure the effect of nutrient distribution and retention through the growing media in any experiments with this irrigation method?
No. Go ahead, Mark.
No, we have looked at nutrient retention, and what we have found basically is that with controlled release fertilizer, you can cut the fertilizer rate by roughly 50%. With water-soluble fertilizers, what we have seen is that you cannot change the concentration of the fertilizer that you are applying, but because you irrigate much more efficiently, you apply a lot less fertilizer solution. So you're still reducing the total amount of fertilizer you apply because you simply water less. So I feel pretty comfortable to say that you can probably cut fertilizer applications in half. We have not looked at fertilizer distribution within containers.
Okay, well, gentlemen, that's all the questions we have, and I'd like to thank everybody who viewed the webinar for joining us today. Be watching out for upcoming webinars, one in November, and we'll be also scheduling webinars for the spring months as well. So as I mentioned before, we will be we did record this, and we will have this posted on our website, e-GRO.org. As soon as we can get it up there. So with that, I'll end things. Thank you very much, everybody.